Hi there, my name's Dave Scarlett and this is my entry to the MIT 6002X Circuits and Electronics Classmates Contest for Spring 2013. I'm going to be talking about options for light-emitting diode drive circuits, so we'll go through a few common arrangements and discuss the advantages and disadvantages of each. Now, I'll mention up front that I'm no expert and I am mindful of the Dunning-Kruger effect, so if I make any mistakes, please let me know in the comments and I'll make corrections where I can. Okay, so the reason why we need a drive circuit for an LED is that it is a highly nonlinear device. This is the VI characteristic of an LED. So we have this VF point here, the forward voltage, and that's the voltage at which the current will suddenly massively increase. We've also got a desired forward current, IF, and what we need to do is control the device in such a way that we end up operating at that precise current. If we were to just put a voltage source, Vs, directly across the device, infinite current would flow, or perhaps more realistically, current would increase until the device exploded. So we need some way of limiting that. Now, the first circuit we'll look at is the simplest and the most common, just a series resistor. So that resistor in series with our LED limits the amount of current that can flow through the circuit. Now we'll solve this circuit to get a value for our resistor. I'm going to start by using the graphical method as described in lecture S6V6 of 6002X, but I'll skip through a lot of the math. So all we need to do in order to calculate where our circuit will be operating in terms of voltage and current is draw a load line across our VI characteristic for the LED. So we just draw a line from current equals Vs on R, up here, current equals Vs on R, to voltage equals Vs. And the intersection point is what the operating current and voltage of our LED would be. So, there's our intersection point, approximately at IF. And you can see that by selecting values for R and Vs, we can adjust this line, adjust the angle of it and move it back and forth in order to select our ideal intersection point with the characteristic of the LED. And that lets us choose the current we want. So to calculate the value of R, we'll go through some quick math. We'll start with the supply voltage of 4.5 volts. As would be provided by 3 AA or AAA batteries. And next we need to know the forward voltage of our LED. So for that I've obtained a data sheet for my specific LED. Here we have it. It gives us some absolute maximum ratings, including a forward current, maximum 30 milliamps, which is also of interest. But as for our forward voltage down here, it lists a minimum of 2.8 volts, typical value of 3.2 volts, and maximum of 3.6. And that's at a typical forward current of 20 milliamps. So any individual sample of this LED could have a forward voltage anywhere in this range. You might test one and find that it's 3.2 volts. You might test another and find that it's 3.4. You really don't have any way of knowing without actually measuring each individual LED. And that's not really convenient if we're going to be building more than one copy of a circuit. But first of all, let's look at the typical value of 3.2 volts. So, fairly simple application of Kirchhoff's voltage law and Ohm's law for our circuit here in order to find R. I've assumed a 20 milliamp desired current there, and that gives us a 65 ohm resistor. But you saw from the data sheet that the actual forward voltage of the device could be as low as 2.8 volts. And if we take this line here and shift it to the left, like this, you can see that the intersection point is rising. So IF is increasing, you're getting more current than you'd actually designed for. So if you designed for a forward voltage of 3.2 volts and your device turned out to actually have a forward voltage of 2.8 volts, you could potentially blow up the LED. So to avoid that, let's be conservative and do it again, but this time using the minimum forward voltage of 2.8 volts. Also, since we've got quite a bit of safety in that we're assuming the minimum possible forward voltage, we'll use the maximum allowable forward current of 30 milliamps in our calculations. And there we go, 30 milliamps, 2.8 volts, and that comes out as requiring a 57 ohm resistor, which is actually a lower resistance than our initial value. So this would in fact give us more current for the same LED. But there's another unknown as well. Resistors do not have exact values. They come with a tolerance rating, and a typical tolerance is 5%, meaning that their actual resistance could be 5% higher or lower than their rating. So we'll need to assume that our resistor could turn out to be up to 5% lower than its rating, and to counteract that, we'll add an extra 5% to that to get an actual resistance value that we can use. There we have it, 57 ohms plus 5% gives us 59.5 ohms. And since resistors come in discrete values, the closest, or rather the next highest resistor I have available is a 68 ohm resistor, so we'll go with that. And as it happens, that's actually quite close to our initial resistor calculation. Okay, so here is my completed circuit. I've got my LED here, resistor, that was the 68 ohm, and a couple of different options for my power source, each of which has 3 AA batteries. Now, the reason I have 2 different battery packs here is to demonstrate a problem with this design. First of all though, we'll turn it on. So, there we go. That's currently running off the battery pack over here, which has 3 alkaline batteries in it. Now, alkaline batteries have a voltage of 1.5 volts per cell, so that's the 4.5 volts we used our calculations for. But I also have some nickel metal hydride rechargeable batteries here, which have a nominal voltage of only 1.25 volts per cell. So the problem I want to illustrate here is, let's say we're trying to build this LED into a torch or a flashlight for the American viewers, and we don't know what sort of batteries the user is going to put into it. They could go with the 1.5 volt batteries, or they might use something with a lower voltage. So if we switch over to the other battery pack, you can see there's a slight reduction in the intensity of the LED. Dims very slightly as we go from 4.5 volts there to 3.75 volts there. So that's a weakness in this design. If the power source changes, then the output changes, and that's not desirable. So we'll look at some improvements to this circuit which will avoid that issue. First of all though, let's take a look at where the power is being consumed in this circuit. I will switch that to the 4.5 volt source, and I have a multimeter here, so I'll turn that on to voltage. It's not zeroing for some reason, but let's not mind that for the moment. And let's inspect the voltage over our LED. So that is 3 volts. And now we'll check the resistor as well. 0.8 volts, which adds up to 3.8. And I suspect I've actually selected the nickel metal hydride cells there. So let's switch it back. That should be alkaline. Now I have a 3.2 volt drop over the LED and a 1.4 over the resistor. So we can tell from that, because the current is the same through the resistor and the LED, that about a third of the power from the source is going into the resistor, and only 2/3 is being consumed by the LED. So our circuit here is really only about 70% efficient. So let's see if we can do any better than that. So the next design we'll consider is going to be a constant current driver, which should provide the same current to the LED regardless of the source voltage. But before that, I need to introduce you to a component you may not be familiar with, which is the bipolar junction transistor, or BJT. Now, BJTs are transistors like MOSFETs, but there are a few big differences. First of all, in the labeling, where a MOSFET has gate, drain, and source, a BJT has base, collector, and emitter. Now, the major difference is that in a MOSFET, the current permitted to flow from drain to source is controlled by the voltage across gate to source, and negligible current enters the gate. Whereas in a BJT, the current permitted to flow from collector to emitter is controlled by the current entering the base and exiting the emitter. So where the MOSFET is a voltage control device, the BJT can be thought of as a current control device. And where the MOSFET ideally doesn't allow any current to enter the gate, in a BJT, the current flow is controlled by current entering the base, and the voltage from base to emitter is a relatively constant 0.7 volts. The base emitter junction here actually forms a diode, so once the voltage across that reaches 0.7 volts, huge amounts of current can flow through the base. Now for our current driver circuit. Now, this is a fairly common design for a current driver, although this particular drawing came from the website PCBheaven.com in an article titled LED Driving and Control Methods by Giorgos Lazaridis. So what we have here is a MOSFET. You might not recognize this symbol, but that's an alternative symbol for the MOSFET. You can ignore this diode on the back there. That's actually part of the symbol, and it just tells us about the behavior of the component under a negative VDS. The other symbol over here is the BJT I just introduced, and then we have a large gate resistance and a small sense resistance down here. This one's called the sense resistor because it will be used to sense the current passing through it. So firstly, let's consider how this turns on. The gate resistor I mentioned is large, but if the BJT is initially shut off, then the MOSFET gate sees the entirety of the supply voltage, which will cause the MOSFET to allow current to flow from drain to source, and as long as the supply voltage is greater than the MOSFET's threshold voltage, that is. So we need to select a MOSFET and find out what that threshold voltage is as a first step. And I've done exactly that. I have the data sheet for my MOSFET here. If we go to page 2, there we have it, the gate threshold voltage. And that's listed as having a minimum value of 0.8 volts and a maximum of 3 volts. So that's quite a wide range. However, our supply voltage is certainly higher than that, so we're okay. Now, the way current is regulated is through negative feedback. Recall that our BJT's base to emitter voltage is a fairly constant 0.7 volts when the device is active. And of course that's equal to the voltage across the sense resistor because they're both connected to ground. Ohm's law can tell us that a resistance that will give us a 0.7 volt drop across the resistor at our desired current, so that lets us select an appropriate value for the sense resistor, and then any additional current will just spill out there through the base of the transistor. So we're setting a desired current through this branch of the circuit here, just across that sense resistor. And if we're getting too much current coming through the LED, that's going to spill through the BJT. And that's where the negative feedback occurs. For just a tiny bit of base current, the BJT will allow a very large amount of collector current. And as that opens up, current flows through here, it's going to pull the gate of the MOSFET to ground, shutting off the current IDS. So on the other hand, if the LED current is too low, the voltage over the resistor will be less than 0.7 volts. No current will flow into the base of the BJT, causing it to shut off entirely. Voltage at the gate of the MOSFET increases, causing the MOSFET to open, and more current flows. And the circuit will be in equilibrium when the current flowing through RS is the amount that causes a 0.7 volt drop across it. So we can just choose a desired current, then calculate a sense resistance, which will give us that current. There'll be a slight inaccuracy in that, first of all, the current passing into the base of the BJT doesn't actually go through the sense resistor, so it's not included in the calculation, even though it does pass through the LED, but that's going to be absolutely tiny. Probably the bigger variation will be in that that voltage from base to emitter won't be exactly 0.7 volts. Now, we just had an intuitive look at how the current driver circuit operates, but just in case you don't believe me, I'll do the math on it as well. I've labelled some of my currents here, and then we're going to start off with the switch unified model formula for the MOSFET current. And this is described in section 7.8 of the 6002X textbook, Foundations of Analog and Digital Electronic Circuits. And we'll label that equation 1. So, a little bit complicated, but you're used to MOSFETs if you've studied 6002X, so that shouldn't be too unfamiliar. Next, we'll look at the behaviour of the BJT, which fortunately is much simpler, and we'll label this equation 2. Now, beta is the current gain of the device, so it's just a straightforward multiplication of the base current in order to get the permissible collector current. And beta will be in the order of between 100 and 800 for the BJT I've chosen at least. BJTs do tend to have very high gains compared to MOSFETs. So next we can use KCL at this node in order to calculate the current that our circuit puts into the base of the BJT. There's a formula for that. So base current equals IDS here minus the current that is passing down through this sense resistor. We'll label that one 3. And then we'll use KVL to get an equation for the gate voltage of the MOSFET, VGS. So we can use this loop here, either loop there, in order to calculate that. And there's a formula for that. So we've got VS is the same as VDD, the supply voltage, minus the voltage across the resistor, gives us the gate voltage. And then we just subtract the source voltage, which is equal to VBE. We could also do something similar to get VDS, but we'll skip that for now and we'll just leave VDS wherever we find it in our equations. So, back to our MOSFET equation. We'll assume first that the device is operating in the triode region, and what we can do is first insert equation 3 into 2, then that into 4, and then that back into the original equation for our MOSFET, and hopefully that'll give us something we can work with. So, we end up with this very large equation here. And we can neaten this up a bit, so I'm going to try to put all of the IDS on the one side. And after rearranging it, it looks like this. Now, it's still pretty complex and there are many unknowns in here. Remember, our VT was unknown. We haven't bothered trying to calculate VDS, but forgetting all that, let's just look at the magnitudes of these individual parameters. So, first of all, we've got K there, which is a parameter of the MOSFET. 1 over K is about 100. Beta, recall, was fairly large, and the gate resistance is also quite large. If we assume a gate resistance of maybe 5K, then we can expect beta RG to be over 1 million. Then VDS is in the order of 5 volts. There's our beta RG again, over 1 million. VBE is our constant 0.7 volts. VT, it varies, but we'll say about 2. VDS like I said, we could calculate that using KVL, but it's roughly going to be the difference between the LED voltage and the source voltage, so we'll say about 2 volts. Now notice that these terms with beta RG in them just absolutely eclipse everything else. We're talking about values of over 1 million compared with 2.75. So we can really ignore everything in this equation that doesn't have a beta RG in front of it. And so all of these terms drop out, and what we end up with is just IDS equals approximately VBE on RS. So that's easy. Much easier than trying to calculate all of this. And that was for MOSFET operating in the triode region. We could repeat all of this using the saturation region equation instead, but we just get a similar result. What determines whether the MOSFET operates in triode or saturation is actually just how big the supply voltage is compared with the LED forward voltage. Because if you've got a very high supply voltage, then the MOSFET is going to have a greater drain source voltage in order to get rid of that before it hits ground, effectively. Also, one great thing about this simplification is that IDS does not depend on VT, which is fantastic because you may recall from the datasheet that VT really wasn't very well defined. It could have easily varied between different samples of the same MOSFET model, and this shows that those variations won't affect our current. Now, let's figure out what values we want to use for our resistors. You can see I've labelled my transistors here with the actual parts I've selected, but we need to pick values for RS and RG. Now, first of all, one thing you may have noticed is that if we require a 0.7 volt drop across the sense resistor and our LED requires 3.2 volts, that's a minimum of 3.9 volts in total. And recall with our 3 rechargeable batteries, we only had 3.75 volts. So that won't be enough. So we're going to need to bump up that to use 4 batteries instead for a nominal voltage of 5 or 6 volts. So let's select that RS. Now we could use 20 milliamps or 30 milliamps as our desired current for the LED, 20 being the typical current, 30 being the maximum it can handle. So we take our formula for RS, and I've applied it for both the typical current and the maximum current, and there's the resistances it gives. Now it happens that I have a 27 ohm resistor handy, which is right in the middle of those two values, so I'll just use that. Now let's look at this other branch of the circuit for a second. First of all, I want to know what the voltage across this BJT will be when it's wide open, just to make sure that it can actually shut off the MOSFET. According to the BJT's datasheet, the VCE at saturation will be 0.1 to 0.2 volts, or a maximum of 0.5. Also just be aware that the word saturation actually has a different meaning to saturation in the MOSFET. In the BJT, it's when it's effectively wide open and you have a low collector-emitter voltage. So, in any case, 0.5 volts is certainly less than the minimum 0.8 volt threshold of the MOSFET, so we're okay there. So let's select a current through this branch that will shut off our MOSFET. Let's say 1 milliamp to keep power losses low. So as soon as we have 1 milliamp flowing through the BJT, we want our MOSFET to shut off. Normally we'd be operating with much less than 1 milliamp current in this branch because we're not going to be operating with our MOSFET completely shut off. So let's see, in order for the voltage drop across RG to be large enough to shut off the MOSFET, we need a resistance equal to the source voltage minus the threshold voltage divided by that chosen current to get our resistance. So we have 6 volts supply minus 0.8 volt minimum threshold for the MOSFET divided by our chosen current through that branch, IC, gives us 5.2 kilo ohms for the gate resistor. I have 4.7 and 5.6 kilo ohm resistors, so we could use either, and I think I'll pick the 2.7, but it really won't make very much of a difference. So let's put this circuit together and take a look at how it operates. Okay, so here's our completed circuit. Once again, I have two power sources. I have 4 alkaline batteries here for 6 volts, or 4 nickel metal hydrides for 5 volts. As for the components, here is my MOSFET connected between the LED and the sense resistor. And then this one here is the BJT, which is connected to the gate resistor, and that blue wire there connects both of those to the gate of the MOSFET. Now it's probably not immediately obvious which pin is which on the MOSFET and BJT, but the data sheets will tell you that. Now I haven't actually connected the anode of the LED yet because I want to run this circuit through an ammeter first in order to make sure I've got the voltage, got the current calculation correct so that I don't blow up my LED. So let's just try touching that in there. 21.4 volts. 21.4 milliamps. I'll get there in the end. So that's pretty much perfect. That's very close to our typical current of the LED. So let's hook it up and see how it goes. There we go. That looks pretty good. And once again, I can switch between power supplies. I'm currently on the rechargeables. And there's the alkaline. And you can see there's really no perceivable variation in brightness between the two. So that's pretty good. Our constant current circuit is clearly working. So just in case you couldn't make out the circuit from above, here's a different view. We have sense resistor, MOSFET, BJT and gate resistor. Now we'll have a bit more of a talk about this circuit and then look at one more option. But first, let's go back to our circuit diagrams for a second. Now let's just take a quick look back at our original series resistor circuit. Recall that about 1/3 of our power was being consumed by the resistor and only 2/3 by the LED. So let's have a think about how our constant current driver would stack up to that. I'll borrow a trick from Professor Agarwal here and say that you have the opportunity to pause the video and think about this for yourself. See if you can figure out whether this circuit would be any more efficient. And whether or not you've done that, I'll give you the answer. The constant current driver is actually no more efficient than the series resistor circuit. In fact, it's a little bit less efficient. The reason for this is, although this acts as a current source, it isn't a completely efficient current source. What you need to keep in mind is that transistors only consume power. They do not provide it. Even though we may model them as current sources, they don't have any internal source of power, so they're only consuming energy. So power consumption here is actually very simple to calculate. All we need to do is multiply the source voltage by the current drawn from it. And the current drawn is just our selected forward current, same as the series resistor circuit, plus a tiny amount for the MOSFET control branch down here. So even if we pretended that we had the same supply voltage as with the series resistor circuit, this one would consume slightly more power due to the less than 1 milliamp that we're getting down this branch. And yes, the efficiency there is really just the ratio of the LED forward voltage to the supply voltage. So we've got the same efficiency here of about 2/3. However, as we saw, this circuit has the very big advantage of being able to cope with variations in our input voltage. So the circuit's more complicated, it doesn't save us any power, but it is very useful for making sure that our LED gets the correct current for a large range of supply voltages. Now, one more curiosity I might mention about this circuit is how it is affected by changes in temperature. Now, BJTs have a property known as negative temperature coefficient, where as the temperature of the device increases, they allow more current to flow for the same voltages across the device. Now, this leads to a mode of failure called thermal runaway, where they become hot during operation, and so the current passing through them increases, which means they're dissipating even more power, since power is voltage across the device multiplied by current flowing through it, so they get even hotter. And that is a positive feedback loop, which can cause the device to eventually overheat and fail. But let's consider how the BJT is arranged in this circuit. If it does get hot and allows more current to pass through the collector, that will have the result of reducing the MOSFET's gate voltage, which in turn reduces current to the LED. So instead of undergoing thermal runaway, our current actually begins to shut down as it overheats. Now, the BJT wouldn't generate significant heat itself due to the tiny currents passing through it, but if we were to place it on the same heatsink as the LED, then it could act as somewhat of a thermal cutoff for the LED, which I thought was an interesting coincidence. Okay, now we're going to look at one final interesting modification, which is pulse width modulation, or PWM. If you watch the CECC videos from the previous 6002X course, you may have seen this technique used by Alex for speed control of a DC motor. And in a similar application, we're going to use it to control the intensity of our LED. Now, what PWM is where we apply brief pulses of voltage to our device rather than one continuous voltage. And this is useful for modulating devices which only like to operate at one power level, where they can only be 100% on or fully off. So what we have here is an output waveform where we have a brief moment of voltage and then the output is grounded for the remainder of the period. In this example, we are on for 1/10 of the time and off for the remaining 9/10, so we call that a 10% duty cycle. And you can see our period there is 1 millisecond, so we are operating at a frequency of 1 kilohertz. So this allows us to operate a device at 10% average power, but in such a way that the device is only ever receiving full power or zero power. Now, I mentioned before that PWM is ideal for devices that only like to be operated at full power. So, let's consider our LED. If we go back to our VI characteristic graph, imagine we are trying to reduce the intensity of our LED just by reducing forward current. So let's say we're aiming for 10% power. We would need to reduce that current down to 10% of its normal value. And that's assuming, of course, that voltage is held constant. But we see that that's really resulting in our voltage falling off the elbow of this curve into a region where it's very difficult to control. And if we tried to set up our current driver circuit to do that, I suspect the LED would either flicker or possibly not light at all. So, one other thing I'll mention is when I decided to undertake this project, one of the big questions for me was, can I get more efficiency out of my LED by using PWM? Rather than controlling the current, can I just push an enormous current through it, but only for a brief period of time, and reduce the resistive losses in the circuit by connecting it directly to the voltage source, but cycling it fast enough that I wouldn't blow up the device? Then I took a look at the data sheet for my LED. Now we have the maximum continuous forward current of 30 milliamps, but the data sheet also lists a peak forward current that is allowable of 75 milliamps, provided it's at a duty cycle of 10% at 1 kilohertz. So we're getting an extra 150% current there compared with our normal maximum of 30 millivolts, but we've got to reduce our duty cycle down to 10%. So we're not actually operating that anywhere near full power, at least compared with maximum continuous current. So we're presumably losing a lot of illumination compared with operating at a continuous 20 or 30 milliamps. And it does get worse, in fact. If we continue looking through the data sheet, we come to this graph of relative luminous intensity versus forward current. And there's our typical forward current of 20 milliamps. And you can see beyond that point, we're really not getting an increase in luminous intensity proportional to the increase in forward current. So our LED itself is actually becoming less efficient as we increase the current. The increase in brightness just diminishes as we increase current beyond its typical value. So that's another reason why trying to use PWM with high current through the LED just isn't really going to be beneficial. One other thing I'll mention from this graph is that these different lines here represent different light components of the LED output, so we'd probably also see a colour shift if we attempted that. So that idea is not going to work out at all. But we can still use PWM to reduce the intensity of the LED and save power that way. Now, the way we're going to achieve our PWM is with a very old, still very common chip called a 555 timer. Professor Agarwal alluded to this device in lecture S25V19, and now you get to see it. So I found this circuit on Wikipedia in the article on the 555 timer, not surprisingly, and this is a circuit for running the device in what is called the astable mode of operation. And that just means it's going to be outputting a continuous series of pulses rather than a single pulse. We also have formulas given on Wikipedia for the frequency, the high time of that signal, and the low time. So we can use these formulas to determine appropriate values for our resistors and our capacitor in order to give us the frequency and the duty cycle that we desire. Now, if you're particularly astute, you may have noticed that these formulas don't actually allow a duty cycle of less than 50%, as TH can never be less than TL. There are a few ways to get around that. One such way is to put a diode across R2. This way, when the capacitor is charging, R2 will be bypassed, so the capacitor will charge quicker than it otherwise would have, giving us a shorter high time. Then, when it discharges during the low time, current can't flow through the diode in that direction, so the low time, the capacitor takes the same amount of time to discharge as it otherwise would have, and that way you can reduce the high time, making it less than the low time. Now, while this circuit is useful as an introduction to the 555, it isn't actually how I'm going to implement my PWM. Instead, I found a very interesting alternate use of the 555 timer. This circuit came from the same website that I got my constant current drive circuit diagram from, PCBheaven.com, in the article LED Driving and Control Methods by Giorgos Lazaridis. Now, what this circuit does is, instead of alternating between the supply voltage and ground, the output of the circuit is connected to a different pin. It's connected to the discharge pin of the 555 rather than the output. And what happens with the output of this circuit is it alternates between being connected to ground during the low part of the cycle and being open circuit during the high part. So instead of directly driving the circuit itself, where you would draw power out of the 555 timer's output pin, this is just used as a pull down. And so if we take our constant current circuit, there we go, we can take the output of this PWM circuit and connect it to the gate of our MOSFET. So when the PWM signal is high, it's open circuit, so it has no effect on our existing constant current driver. And when the PWM signal is low, it'll be connected to ground. So the gate of the MOSFET gets pulled to ground, the MOSFET shuts off, no current flows through the LED. With no current through here, the BJT also shuts off. So we have only a tiny amount of power being consumed then. We'll have whatever is required to operate the 555 timer, which is fairly small compared with the LED. And then we will have the tiny amount consumed by RG, because current will flow through RG through the 5.5 timer to ground. And that was calculated at only 1 milliamp, so that's quite small. So what we get is, at a 10% duty cycle, we'll have our LED outputting an apparent continuous light at 10% of its maximum output, and the whole circuit will be consuming just a touch over 10% of our normal power. So let's go ahead and implement that and see what it looks like. Before I do that though, one thing I'll just mention, some of the components I'll be using in this circuit, aside from the capacitor you saw in the previous example, this circuit has a trim pot potentiometer here, which is an adjustable resistor with 3 terminals. It acts a little bit like an adjustable voltage divider, and then a couple of diodes which connected to the same pins at this end just ensure that current doesn't just flow through the easier route in this potentiometer. It always goes the same direction. So let's put that together. Okay, so once again, here is our slightly messy breadboard. You may have been wondering what was hiding on the right hand side of it, and now you know. That's our PWM circuit. So we have the 555 timer chip here in a dual inline chip format. There are a couple of diodes in there. There's our trim pot potentiometer and a little, what's that? 2.2 nanofarad capacitor. The circuit diagram actually specified something much smaller for the cap, but I found that was giving me about a 50 kilohertz frequency, which is a little bit excessive. So I used a larger capacitor in order to dial it back to what should be around 1 kilohertz. So let's fire it up and see how it looks. Now I haven't actually connected the PWM circuit yet, so that's just the LED running on our previous constant current driver. But this is the pull-down connection, and I think I'll just attach it to the leg of the gate resistor there, which of course is connected to the gate. And there we go. We saw an instantaneous drop in intensity when I connected that. And I should be able to further adjust the intensity using the trim pot here. There we go. I can almost completely turn it off. So that's looking pretty good. Now, to the human eye, and hopefully to the video camera, this just looks like a continuous output of light, even though it's actually cycling on and off at a frequency of 1 kilohertz. That's easily fast enough that I can't actually perceive it blinking. Now, remember I said that I'd increased the size of that capacitor to 2.2 nanofarads in order to slow down the circuit. I have here a 1 microfarad capacitor, which is 500 times larger than that one. And recall that if I place 2 capacitors in parallel, their capacitances add. So if I place this capacitor over the existing one, the frequency of the PWM should slow immensely. And if it's currently at 1 kilohertz, it should probably drop to around 2 hertz when I connect this cap, which is 500 times larger than the existing one. This is an electrolytic capacitor, so I have to get the polarity right. That's easy. Negative goes to ground. And if I just touch that in there, there we go. So that looks like it's operating at about a 50% duty cycle, I'd say. Let's just adjust the trim pot to make it even dimmer and see what that looks like. There we go. Whoop. Maybe not quite that much. So, whoops. There we go. So you can see there it's only a very brief pulse of light with a longer off period. And the frequency also appears to have slightly increased, as will happen when you change the resistance. So there you go. That's our pulse width modulation circuit for effectively plugging it straight into a constant current driver for an LED. Now, to summarise what we've done, we initially looked at a series resistor circuit. The advantage of this circuit was that it was incredibly simple, but there were significant power losses through the resistor. And the efficiency of this circuit was pretty much proportional to the ratio of the forward voltage of our LED to the supply voltage. So we could have chosen a supply voltage which was closer to the forward voltage of the LED in order to improve efficiency. But the problem with that is our load line would then come through a point very close to our big current spike at VF. And so we would need to choose a tiny resistor which would give us an almost vertical load line. And you can imagine it's very difficult to pick a precise intersection point between this almost vertical load line and the almost vertical VI characteristic of our LED, especially when we don't know exactly where, in terms of voltage, this VI characteristic is going to be positioned. So the next circuit we looked at after that was our constant current drive circuit using a MOSFET and BJT transistor. And this was no more efficient than the series resistor circuit, but it had the big advantage of being able to deal with variations in the supply voltage. So when we switched from alkaline batteries to rechargeables, there was no noticeable difference in the brightness of the LED because this circuit held the current constant through that branch. And finally, we added pulse width modulation, hooking that in to the gate of our MOSFET, and that allowed us to run the LED at less than 100% power. It didn't give any improvements in energy efficiency at full power, but it was very useful if our LED was too bright at full power, or for example, if we were implementing a torch or a flashlight and we wanted a power-saving mode of operation. This would allow us to run our LED at 50%, 25%, 10% light output and save pretty much power proportional to the reduction in brightness of our LED. Now, one final thing I'll mention, just in case you were disappointed by the fact that the PWM circuit didn't allow us to get any extra efficiency out of our LED, I want to show you one more thing really quickly. So, let's say we have our LED here, and let's say we've got a voltage source. Now, notice I've drawn this so that the voltage is actually being applied to the LED in the wrong polarity. But say we have an inductor in parallel with the LED and then a switch. So imagine we cycle this switch on and off at extremely high frequency. What will happen is when the switch is closed, our voltage source applies a voltage to the inductor, causing current to slowly increase. You may recall current through an inductor is proportional to the integral of the voltage, so current will continuously increase. Then we open the switch, isolating the voltage source. Now current was flowing in this direction, so the inductor is going to want current to continue flowing in that direction. So instead of going back to the voltage source, it flows through the LED. Then the switch closes again, and once again our current is going through the voltage source, charging the inductor up. Switch opens, current goes through the LED, causing the inductor to slowly lose its current. And so if we switch that switch at the correct frequency, we could adjust it so that even if our power supply here had a voltage much higher than the forward voltage of the LED, we could use that to power the LED with theoretically up to 100% efficiency. There's no resistors in this circuit. We have no loss whatsoever other than what the LED is consuming. So this is, in fact, well, this is an extreme simplification, but this is the basis of what is called a buck converter. And that's a type of switch mode power supply, normally used as a step-down converter. So it would take a higher input voltage and use that to drive some load at a lower voltage. And so that's a way we can actually increase the efficiency of our LED drive circuit if we wanted to go down that path. But I think the video's been more than long enough already, so I'll leave it at that. That's the video. Thank you for sitting all the way through it. I hope you enjoyed it. I hope you learned something. And finally, thanks to Professor Agarwal and of course all of the 6002X staff for running this absolutely fantastic course. It's been a great experience.